The gravitational potential energy of the ball remains constant regardless of its position. So the graph of the gravitational potential energy of the ball with respect to position is a horizontal line because the gravitational potential energy is constant. This water bottle is in stable equilibrium because its gravitational potential energy increases as its position moves away from the equilibrium position. This is because the center of mass of the water bottle goes up as the position goes away from equilibrium. In other words, the water bottle naturally returns back to the equilibrium position when it loses gravitational potential energy. This dry erase marker is in unstable equilibrium because its gravitational potential energy decreases as its position moves away from the equilibrium position. This is because the center of mass of the dry erase marker goes down as the position goes away from equilibrium. In other words, the dry erase marker naturally moves away from the equilibrium position when it loses gravitational potential energy.
When we move this ball slightly to one side, it will remain in the new position. We say that the ball is in neutral equilibrium. When we move a ball along the surface of a hemispherical bowl, forces will appear that tend to make the ball move farther away from the position of equilibrium. We can therefore say that a ball on the top of a sphere is in unstable equilibrium. When we now move the ball slightly to one side, forces appear that will make the ball return to its original position of equilibrium. We can therefore say that at the bottom of the ball is in a position of stable equilibrium.
Force on the object, then it will start rotating. So twisting force which will produce rotation is called torque.
We must look at it as a rotating object, which is rotating about a fixed axis hinged at one of its sides. For entering a room, we first have to rotate the doorknob, and then you either push the door or pull it depending on the type of the hinge. If you remember what we learnt in kinematics, the word push or pull represents force. We are applying the force on the handle of the door in order to rotate the door, but in this case, the force alone is not responsible for this rotation. There is something else in action here. It is the distance from the axis to the point at which we apply the force. This combination is known as torque.
This animation shows the applied force couple with a distance d between them that equal the applied moment.
Action force, then what will happen? The rotation effect can be occur. This couple effect
is the point where the entire weight of the object appears to act. Working out the centre of mass of a symmetrical object is easy. It's simply where the lines of symmetry cross. However, it's very unlikely that you'll be dealing with such perfect shapes, so you work it out by suspending the object freely along with a plumb line. The centre of mass is always below the point of suspension, so by marking the vertical along the plumb line, you know that the centre of mass is somewhere along that line. By suspending the object from another point and repeating the process, you get two lines that intersect, and the point of intersection is the centre of mass. The position of the centre of mass is very important when it comes to the stability of an object. For example, a double-decker bus is built to have a very low centre of mass and a wide base, so that the line of action of its weight stays within the base when it goes around a sharp corner. If something has a high centre of mass combined with a small base, then it's very unstable and will topple over with minimal effort. A plumb line is an example of a simple pendulum. All it consists of is a weight attached to a piece of string that can swing freely. The time taken for it to swing from one side to the other and back again is called the time period. The time period of a pendulum of the same length is always the same no matter what height you release it from.